Hello, and once again, welcome to another session on organic spectroscopy problem. This time, I have taken a very simple problem to calculate the J values involved in four different compounds: vinyl chloride, vinyl acetate, methyl acrylate, and allyl chloride, and to assign the peak positions to the respective protons. It appears to be a very simple problem because these compounds are very simple, but you will find interesting observation, particularly in methyl acrylate and allyl chloride. And I have taken these two simple compounds just to evolve the topics for the graduate level students. And these programs, as you know, are meant for graduate level students, research scholars, PhD students, and maybe undergraduate level students, if interested, can take the benefit of this program. Now, let us talk about vinyl chloride, the proton-NMR of vinyl chloride. If you look to the structure of vinyl chloride, there is nothing other than three hydrogen. These are the three ethylenic hydrogens. sp2 hybrid carbon is there, so we involve three J values, as possibly all of you know that one will be the highest J, that is the vicinal trans, J3 trans, which should be greater between 12 to 18, then vicinal cis between 7 to 12, and geminal coupling here is very small, 0 to 2. Therefore, each peak will be a doublet of doublets, DD. Coupling, supposing HX first couples with HB with a greater coupling constant, say 16 Hertz, and then each component further splits into a doublet by coupling with the J3 cis of say 10 Hertz. So same is the case with this. This will involve small geminal coupling of about 1 or 2, and this will involve the middle one, the intermediate 10, and this will involve the highest 16, for example. And in fact, the peak position assignment will be unequivocally done by finding the J values with the first-hand knowledge that J trans is greater than J cis and J2 is very, very little. For the beginners, let me remind you that for this vinyl system, these two protons HA and HB, they are not shift equivalent because they are not interchangeable by any symmetry operation. So they give two different peaks. Now, and for the beginners who are maybe undergraduate or graduate level students who have not acquainted with how to find the 2J values for a DD, because a DD involves 2J values. So this is one finer doublet, the other finer doublet. So between each finer doublet, this is the lower J, say J2, smaller J. And between the two midpoints, it is the larger J, J1. We have taken J1 greater than J2. And if I number the peak positions 1, 2, 3, 4, then 1 to 2, 3 to 4 will give you the smaller J. And 1 to 3, 2 to 4 will give you the larger J. And we can every time average if the two values of each type comes a little different, which usually appears for experimental errors. So we have to average it. We show you the peak, but the peak is clumsy. This HX peak, which is at the most distilled position of 6.26, as it is close to chlorine. The DD, the four lines are jumbled up, clumsy, but the good news is that we have the data, which we have obtained everything from the source chemical book, which is an authentic source for Proton-NMR and the data set of all the lines. So you find all the lines of HX in terms of Hertz, from which we find the J value, and in ppm, which will be used to find the average for the peak position, and the intensity, relative intensity of the four lines, which also indicates it is a 1:1:1:1 dt approximately. We can't expect the intensity to be exactly 781, 781, 781, 781. It will be always some fluctuations, but intuitively it is 1:1:1:1. So, and these are 8 lines. There are 2 dd's, one for HB. The next peak closer to chlorine is 5.47 ppm, and the least distilled is 5.39. These are the ethylenic protons, which appears between 4.5 to 6.5, right? But let us assign why it is 5.47. Why this is 5.39? You can yourself assign looking to the J values. Now we have found the J values for HX data. This minus this, this minus this will give you the 2 smaller J, in this case 7.49, and 1 to 3, 2 to 4, you get the larger J. Since you are getting the 2 larger values, a geminal coupling is less than 2. So not getting geminal coupling, so therefore it is unequivocally, it should be HX, which involves the larger J and then the intermediate J, not the geminal J. So we assign the 6.26 peak to HX. Then let us look to the lines of HB. Why it is HB? Because the similar manner, when we calculate the smaller J and the larger J, we find 14.4 and 1.4. That is only possible for this, because the same 14.4 we have already got for HX and also for HB. So this peak, which we have designated as HB, is 5.47 for the HB. Similarly, when we calculate for HA, we find the same geminal coupling constant, the smaller one, 1.4 approx, and the same J3 cis of 7.5. Similarly, vinyl acetate is very similar, excepting that the delta values are little different. This is very more distilled, going to 7.28, because it is oxygen, not chlorine. The same pattern will be found. This is most distilled. The data, those are given, they are not been expanded, so these are jumbled up. This is a DD, this is a DD, this is a DD, but we can't see 4 lines in each case. And this is a singlet for this methyl at 2.13, an additional singlet here. But the good news is that data is available. So in the similar calculation has resulted, the 7.28 peak involves the 2 larger coupling constants, so undoubtedly it is for HX. And for HB, we involve the geminal 1.5 and the largest coupling constant. So it has to be HB, 4.88. This. And for HA, it will involve the intermediate J3 cis and the J2, small J2, geminal. Therefore, we have not only assigned the peaks correctly, but also we have found out the J values from the data set and averaged for the trans cis J3 and J2. Now the interesting example of methyl acrylate will come. If you follow the same principle that we adopted for vinyl chloride and vinyl acetate, we will be giving this to be the most distilled, followed by this, followed by this. So never ever jump into conclusion that every molecule will follow the same pattern. But see, the difference was in vinyl acetate, here was oxygen, or in vinyl chloride, here was chlorine. But here is his C double bond O. It is the ester of acrylic acid. You will find the most distilled peak is not HX, it is HB. Very interesting. And if you are a teacher, you are watching this, if you ask to your undergraduate or postgraduate students or graduate level students, I doubt whether they will be able to answer that this is the most distilled peak, unless otherwise they are given provided the J values. They will calculate the J's and then see which is for which. Now I will explain to you why HB is in the most distilled position. Same, the proton-NMR peak spectrum is not having much clarity here. These are all DDs, but the list, the most distilled peak is for HB now, and the intermediate peak is 6.12 is HX, and the least distilled peak is HA. This is surprising. These two protons, one is the most distilled 6.4 and the other one is the least distilled 5.82. Why? Of course, this is a singlet at 3.79. Of course, another peak is appearing, that is an artifact for the impurity or something. We don't bother about this. And now, looking to the HB, first we have calculated the J values for HB. We found that it involves the highest trans J3 and the small geminal. So which one is involving geminal as well as trans vicinal? This is this one, which is closer to C double bond O. And then we found for the HX. Why this is HX is 6.12? Because it involved the larger coupling constant. We have found out in the similar manner 17.35 and 10.4. Undoubtedly, this is for HX. And HA, you will be finding the geminal as well as the cis vicinal 10.4 and 1.5. And let's see what is the reason behind it. The predominant reason behind it is the diamagnetic anisotropy effect of this carbonyl function, the pi electrons induced current in the presence of external field and the induced magnetic field that it will generate. You will have the induced magnetic field will have, if you develop cones, it will have a shielding cone and a deshielding cone, and this being nearer falls in the deshielding cone of the carbonyl group's induced magnetic field, the diamagnetic anisotropy. And I have shown you an example to recapitulate your memory as to what is the effect of diamagnetic anisotropy. For example, acetophenone, the two orthoprotons have unusually large dishielding, exceeding 8 ppm for both. Not para. Para comes next. It is not because of resonance alone, but because these orthoprotons, they fall in the deshielding cone of this carbonyl function's induced magnetic field. Now, similarly, another rotamer can be, this is a single bond. You can have another rotamer conformer to show that this proton also falls in the deshielding cone. Same is happening here. Resonance is not at all a guiding principle here. Had it been, the resonance been, or the conjugation between these two pi bonds being the guiding principle, then these two would have been closer. But here this is the least deshielded and the intermediate deshielding is HX due to minus I effect of this. As usual, what happened in case of vinyl chloride and vinyl acid. But unusual high shielding of this is due to the diamagnetic anisotropy effect of C double bond O. Is it not interesting? So, in my programs, I used to train the graduate level students, research scholars, how to calculate the J values and how to take a pragmatic approach to solve spectroscopic problems. related to organic molecules. Now, let us come to the climaxing allyl chloride. In addition to the vinyl system here, you have another CS2 that makes it allyl. And allyl has a long range coupling, J4. In addition to J3 trans, J3 cis, J2 geminal coupling, you have J4 coupling, which is, coming into force in these systems, allylic, homoallylic, propargylic, and aromatic systems, and many other systems, strained systems that you know. So in this case, allyl chloride will involve minimum of 4 coupling constants, maybe 5. One is J3 trans, J3 cis, second one. The third one is geminal, third. And the fourth one is this J4, and there might be 2 J. With respect to this, it may be J4 cis, J4 trans. With respect to this, we can have different J values coming from these 2 protons if they are non-equivalent. That depends on the dihedral angle between the CH bond and the plane carrying the 3 carbon atoms. So all these are very fortunate when this is a rigid system, cyclic system. These 2 are non-equivalent, a rigid system. Then these will couple differently, slightly differently, and that coupling can go up to 3 in the strained system, this allylic coupling. And if the dihedral angle is 90, it is still more. We're not going to discuss about the J4 coupling in details. But here, since it is a carbon-carbon single bond, it's not that much rigid. Of course, chlorine is little bulky, so there will be some rigidity of the rotation of this single bond. We might expect 2 different J values, J cis, J trans, or the 2 allylic J values. But for all practical purposes, we will be taking only 1 J value. But theoretically, there can be 2 J values, because we can't find them in our data. As we will continue to discuss this. Now, coming to the NMR spectrum, the Proton-NMR spectrum, which is from the Aldrich source, a much more authentic source, Aldrich chemicals. And I have borrowed this from my friend Professor James Novick of UCI, University of California, Irvine, US. He has expanded all these 4 peaks. In fact, there are 2 peaks here, 1 peak here, and 1 peak here, 4 peaks. He has expanded all the 4 peaks. This is for HX. We'll see why it is HX. And the expansion is here. I will show further, expansion by zooming it. And this is for HB. This is HB. This is HA. Expansion here in the original spectrum. It carries a little diagnostic value, but once we expand it on a computer, you can see its interesting line positions and the pattern, recognition pattern, with the peak recognition pattern. And this is the CS2, the allylic CS2. This is expansion. This and the corresponding integral peaks are given. This is for 1 proton, this is for 1 proton, this is for 1 proton, and these are for 2 protons. Now I am showing you at this moment the expansion. Lest I forget it, let me show you the expansion. This is the peak for HX, which contains 10 lines. In the approximate intensity ratio, just remember 3:1:1:2:3:1:1. This appears to be 3, little more than 2, but this, since it is a centrosymmetric peak and some non-fast order nature might be expected, so therefore it looks little more, but it should be taken as 2. 1:2:1:1:2:3:3:1:1:2:1:2:1. So this is the 10 line spectrum. You just remember 10 line spectrum. And this, if you can minutely mark, this is a doublet of quartets, DQ. Because each one is a quartet. 1 is to 3 is to 3 is to 1. 1 is to 3 is to 3 is to 1. There is the overlapping of lines, blurring of lines, because, I'll tell you the J values are very close. And this is also the peak for HA is a doublet of quartet, DQ. And since the J value is small here, so this is a very jumbled up quartet. 1, this appears as a solder. 1 is to 3 is to 3 is to 1. 1 is to 3 is to 3 is to 1. This is also a DQ. This is a DQ. And I will tell you this is a DDT, doublet of a triplet. Doublet of doublets of a triplets. That has been turned into a 10-line pattern. I will explain to you why. And this peak is the CH2 peak, which doesn't appear anything significant if you look to the original peak. But once you look to the expansion, you find it is ADT, doublet of triplets. One triplet is 1 is to 2 is to 1. The other triplet is 1 is to 2 is to 1. So there are 2 triplets here. So this peak is a DT. A peak for HA and HB, each is a DQ, doublet of quartets. And this peak for HX containing 10 lines is a DDT, doublet of triplets, turning into 10 lines. And now we will prove that. How? So these are the expansions and these are the real peak positions. Let us talk about HX. Now, HX is a DDT. Why it is a DDT? Because doublet with the trans J3 coupling, then cis J3 coupling, doublet of a triplet. Because these 2 protons are to be taken as virtually shift equivalent because of rotation and therefore triplet. So DDT. But what happens here, DDT should contain 12 lines. 2 2s are 4, 4 3s are 12. But we are really getting 10 lines with a very interesting intensity ratio, as I've already told you. Now I'm just giving you the splitting tree with a typical case when the higher J, that is J3 trans, we call it J1, is equal to the sum of the 2 lower J's. This is the intermediate, this is the smallest J. So if the largest J is approximately equal to the sum of the 2 lower J's, then something happens. Overlapping of lines appear to reduce the number of peaks by 2. So 12 lines turn into 10 lines. I'll show you. Supposing here I have simulated this pattern. I'll show you by taking the largest J as 16, the intermediate J as 10. This is the trans J3, this is the cis J3, and the other J3, the allylic J3, I will show you, is 6. It cannot be geminal coupling, J3, 6. So these are the 3 J values, and the J1 is equal to the sum of J2 and J3. In that case, what happens here, I have used a graph sheet. The beginners, they should use a graph sheet in a computer to know where are the overlappings happening. Now see, this is 16, this is 10, 5, 5. And once you go for the triplet, doublet of doublet is over. This position is DD. Then when you come to DDT, you make this line as a triplet, 1 is to 2 is to 1. 1 is coming here because this is 6, this is 6. And when you make this a triplet, 1 is to 2 is to 1. And when you make this a triplet, its 1 is coming here. 1. So 2 plus 1, 3. And 2 is coming here. 2 plus 1, 3. And its corresponding 1 is coming here. 1 is to 2 is to 1. And when you make this a triplet, its 1 is coming here, 2 is coming here, and 1 is coming here. So what you have found? You have found at this position a crossover of lines happening. This is the sibling of this triplet is crossing beyond the sibling of this triplet. Same thing happens here. The sibling of one triplet crossing over the sibling of the other. And here, the siblings of two different triplets, they overlap exactly, because this gap is exactly 6. If 5 will go here, 5 will go here, 5, 5, 10. So 6 will remain. So this will definitely fall on this, and you are therefore getting the intensity ratio 1:2:1:1 sequentially. 1:2:1:1, 3:3:1:1:2:1. That what we are getting, a centrosymmetric, beautiful peak pattern of 10 lines. Is it not interesting? Now I have simulated this particular graph, a particular peak pattern, by using a software developed by the same group, Professor Norwick and his team of UCI. They have generous enough to share with me that particular software package, which you can get from other source also, but I'm using theirs. I'm showing you here. This is the software, Excel software that they have developed to immediately put the J values and simulate the peak pattern. I am putting here the J1, 1J, I say 16, and the other is 10, and the other two, because it will be a DDT, there will be two which will be having the same coupling constant, 6, 6 each. In that case, you will be getting the same what I have drawn there. I have just copy pasted from here. 1:2:1:1:3:3:1:1:1:2:1. And to find out, let me show you how to find out the J values. The lowest J, say 6, the lowest J is between 1 to 2, between their siblings of each triplet, 1 to 2, 2 to 4. These are the sequential numbering of peaks from left to right. 1 to 2, 2 to 4, 3 to 5, 5 to 6, then 6 to 8, then 7 to 9, 9 to 10. These are the maybe 7 values of the lowest J. You can average if they will come different, slightly different. And the middle J is from the midpoint of the first triplet, midpoint of the second triplet. So midpoint here and the second triplet is here. So 2 to 5, or you can go 1 place to the left. 1, 2, 3, 1 place to the left. The left of this sibling, of this green sibling is here. So 1 to 3. Similarly, you can go for 2 to 5, which I already told you the midpoint. You can go 6 to 9, the midpoint. You can go 1 place to the right, 1 place to the right, this one, and here 1 place to the right, this one. So 8 to 10. We have 4 different J2 values, I mean the intermediate J values. And the highest J value is the midpoint of the pattern is here. The two triplets, the crossover of lines occur here. So the midpoint of the crossover of lines is the midpoint of the two triplets. And these two triplets, the midpoint is here. So between this to this. So the best is you have to go 1 place to the left, just immediate left. That is peak number 3, peak number 7. So this gap is the biggest J, and so 4:8. So I have taken only 2 values, 3 to 7, 4 to 8. Some other time I will explain how we can also find out the J values by reduction method. First, just by eliminating first DDT, eliminate T by averaging all the triplets. Then eliminate D by averaging all the doublets. Then finally you are left with only D and take that to get the highest J. So this is called the reduction method developed by Professor Hans of Wisconsin University. I have also equal fascination to use the reduction method wherever I find this peak separation method bit difficult or bit confusing. Now we will take the data, the 10 lines. You can see interestingly, I have not given you the data set for relative intensity because I have shown this in this. So the relative intensity data also has given. I have just avoided that data sheet to avoid delay. You will find the same ratio: 1:2, 1:1, 1:3, 3, 1:1, 1:2, 1. So that confirms the DDT pattern turning into 10 line pattern. So when you find, as per these separations I have told you to find J3, J2, J1, you are finding 7 J3 values. I mean the lowest J, which average is 6.5 approx, and the intermediate J, this is J3 cis, this is J3 trans. So obviously these three values of about 16.9, 10.1 and 6.5, it is only this HX is involved. This is 16, this is 10, and this J3 is about 6.5. So that you are getting, and approximately the sum of these two is approximately equal to this, approximately. So there will be overlapping, although not exactly coalescing, but overlapping very closely to give a 10 line pattern that is really a DDT, right? This is the 5.93 peak is for HX. We have found that. Similarly, we can go for HB. HB is very interesting. I told you it is a DQ, doublet of quartet, but it should be ideally a DDT. Supposing we take HB, it should be D, then D, and then J4 coupling is another D. T. I'm sorry, there are two J4 couplings, two protons. DDT. Maybe DDDD, because if these two are different, had it been a strain system, or it will give DDD. D, 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 4 Ds. But these two are equivalent, so we say D, D, T. But here it is turning into a DQ. There DDT was there, but giving 10 lines because of overlappings. But here it will be turning into a DQ. Why? Because if J2, the small geminal coupling, will be approximately equal to J4, then for this you have to add up this and these two, 3. So first doublet, and for these 3, the quartet. 3 protons, it will be a quartet. First doublet, then for 3 protons, it is a quartet. So doublet of quartets we are getting. I had shown you the expansion. So you know how to calculate the 2J values, because here virtually 2J values are involved. 1 to 2, 2 to 3, 3 to 4. 5 to 6, 6 to 7, 7 to 8. This will be the lower J value. And then from the midpoint to midpoint means 1 to 5, 2 to 6, 3 to 7, and 4 to 8. So we have used these data set from the same chemical book source, and these are the line positions. Average is 5.31, and we are getting these two 16.9, the same one that we got here, that is the trans vicinal coupling, JBX, and this is the geminal coupling, which is nearly equal to the allylic coupling, right? That is why we will assign the value 5.311 to this proton closer to the CS2Cl, because it involves 16.9, and this one J2 and J4, they're equal. That is why HB. Similarly for HA, in the similar lines, it should be a DDT, but turning into a DQ. And all these 8 lines, DQ means 8 lines, which we have got for both HB and HA. We calculate them in the similar manner. We find a J value of 10 and 1. So the 10 is due to this, and 1 is due to this as well as this. Is D for this 1 plus 3, 1 plus 2, 3, 3 plus 1, 4. So DQ. So we have unambiguously assigned the peak positions. This is 5.3, this is 5.93, and the least distilled is HA 5.16. But what about CS2Cl? CS2Cl, ideally it should be a D, D, D. But since the allylic coupling is taken to be 1, no cis trans, they are very close. So these two will be counted together as 2. So it will be a dt. So I have simulated in the same software to how it looks like a doublet or triplets here with a little greater value of the smaller constant. Otherwise, it will be so close, it appears less aesthetic value. So now we have calculated using the real data. We found that the higher value 6.5 nearly, and the lower value is a lot of discrepancy has come, and the average is 1.1. So that 1.1 is due to this, which you are getting almost the same value in other systems involving J2 and J4, and the other one is 6.5. That is this one, which we had also got for HX 6.5. So we can get the grand average. Trans J3 we're getting 16.9, cis J3 we're getting 10.09, and the CH2 we're getting 6.47. But for the geminal coupling and the J4 coupling, since J4 can be two different values, so ornamentally we have chosen to present three values that we have got. Instead of averaging, here we got 1.003, here we got 1.115, and here we got another value. This is 1.321. So these three smallest values we have proposed. One could be for J2, geminal coupling, the highest value, and the two allylic can be 2. Of course, in allyl chloride that might be 1, but since chlorine is a bulky group, there might be restriction in the rotation. So for the alkenic protons Ha and Hb, there might be two different coupling constants, cis and trans. So one of them for the cis, the other one for the trans, but we could have averaged them also to show that all these three are equal. Why we gave three different values? Because they are really different, and we are not getting a good coalescence overlapping. We are getting a partial, most overlapping, and therefore the DQs are looking little blurred because of this overlapping. And sometimes I have not shown you the intensity. In DQs, it should be 1:3:3:1 for each quartet. But sometimes you are not getting 1:3:3:1. You're getting little more than 2. But these are, due to the presence of some non-fast order nature, or maybe due to partial overlap, not full overlap, so that the line broadening happens, so the height is reduced. But the integral peak is for all the lines of that pattern. That is there for 1 proton, 1 proton, 1 proton, 2 protons. But the line height might be reduced if there will be partial overlapping. 90% overlapping, not 100% overlapping. So how did you like? This is all about the allylic chloride, and we have seen the interesting methyl acrylate. These two are really interesting, but we started with vinyl chloride and vinyl acetate just to introduce into the J-cis, J-trans, vicinal, and J2, DD, and then talk something very unusual, methyl acrylate, where the least distilled is having the nearest most distilled. Right? A, B, one of them, we have taken B as the most distilled, closer to carbonyl group, and the least distilled is A. And the intermediate, more than 6, it was HX, closer to the carboxylate function minus I effect. So if you have liked this video, you don't hesitate to hit the like button. And if you have not subscribed, please subscribe so that I will be motivated to produce more and more such videos on organic spectroscopy, which is my hobby, my passion, and I am continuing to study often that subject. I'll be of use to you. Bye-bye. See you in my next video.